Hello, this is my Physics 2212 Lab 5. So in this lab, what we did was we placed a magnet inside of aluminum foil and we observed what happened. So the purpose of this lab was to see what effect the aluminum foil had on the bar of magnet as it was falling through. The result that I got was that the magnet took 0.23 seconds to completely go through the aluminum foil. So there were two main fundamental principles involved with this lab. We have Faraday's law, which was used to find the current in the loops of the conducting tube, as well as the Biot-Savart law, which was used to find the magnetic force and field as the magnet moves throughout the tube. So we used two different types of materials for this lab. First, we have the magnet, which is shown in this picture, as well as the aluminum foil, which is shown in the picture above. As for the procedure, it was really simple. We just set the aluminum foil up vertically, and we dropped the dipole through, the magnet through, with the north end facing the bottom. This lab was really code heavy, so I'll just walk through each part of the code. So lines 33 to 38, what we did is we set up our constants. So L here is the length of the tube, or the aluminum foil. So this is 0.3 meters. Also found the width to be 0.025 meters and the inner radius to be 0.02 meters. For lines 72 and 73, what we did is we found the mass of the magnet to be 0.025 kilograms, as well as the magnetic dipole moment from lab 3, which is 3.1. Also from lab 3 is the dipole B function here in lines 98 to 102. So what this function does is it just finds the magnetic field due to the dipole. So for parts 115, lines 115 to 122, we just found the change in flux with respect to time with two inputs, the magnet and the ring. Then for lines 158 to 160, so this is the Faraday's law part of the lab. So Faraday's law says that EMF is equal to the change in flux with respect to time. And then we also know that EMF, or potential, or V, is equal to IR. And then if we divide both sides by R, then we get current is equal to change in flux with respect to time divided by the resistance. So for this part of the lab, we use the force on the magnet by the tinfoil from part 2, as well as the current induced, which we also found in part 2. So what we do here is we find the magnetic field on the tinfoil. Then after finding that, what we did is we found the force on the foil by using the equation FB is equal to I delta L cross B. Once we run our glow script model, we have this shown in the right. So the glow script model predicted that it would take 0.118 seconds for the magnet to fall through, which was fairly close to the time that we got, which was 0.23 seconds. Although it may be twice, we're dealing with really small numbers, so I'd say it's pretty close. If you notice the graph, you'll see that there's time from 0.02 seconds to approximately 0.11 seconds where the velocity is constant. So this is the time that the magnet is completely in the aluminum foil. So we know that it's constant here because there's no net force. Therefore, the acceleration is 0. So some reflection questions. So what if the resistivity of the conductor were reduced as close as possible to 0? How would the dynamics of the falling magnet change? Well, if the resistivity were 0, then it would lead to like a larger induced current. Therefore, it would take longer for the magnet to fall through. Then part 2, if holes or slots were cut into the tube, how would this affect the ring currents in your model? So if there were holes or slots, then that would mean that there's less complete loops, and then that would also mean that the induced current would be smaller. Therefore, the magnet would fall through faster. So thank you for listening to the lab.